Yeah, good. Let's record. So yeah, so we haven't looked at like the core, the guts of the JITifier. How do I create a kernel? Um, how do I hash it? How do I compile, how do I compile it, load it in? How do I verify it? Make sure it hasn't changed. Because I worry about, well, what happens if you create an operator called add Gauss? I've got an example, say the Gauss demo. Add two Gaussian integers. What if you decided and you did this a week ago, and you change your code and you change the definition of but you don't change the name. And I think, oh, I've got add Gauss here. Here it is, blunk, and it's the wrong string. Okay, well, that's not good. I check for that. Um, and so we could talk about that. I could show you more about, the whole space of where the JIT needs to extend. I got to do more with the JIT in the future. It really depends on the accelerator that's backing GraphBLAS. If it's an accelerator that's happy to have some kernels running on the host or on the CPU, like a CPU cores that are sitting on a accelerator with, say, FPGA cores or something like that, FPGA resources, and you can easily go back and forth, and you don't have to have accelerations for everything. So, but there are some kernels I need to JIT, and so how do I define the operations, the macrofication process, create the header? How do I do that for both CUDA JITs and OpenMP JITs, which are practically identical, actually, very similar. So those are the things I have not done that I could do today.
Yep.
So let me, is this font, maybe make it a little bit bigger? Whoops.
They show up pretty good on the video.
Do they? Okay.
Yeah,
Is this,
it's
does
about
this look,
the minimum size possible,
because
but
I
it
could
does.
make it a little bit bigger if that would help, like this.
It might make it easier for future
Mm-hmm.
video watchers. Yeah.
Okay, let's go with this size of things. Okay, so we're inside. See if I'm up to date here. Yeah, we're inside the dev3 branch, which is the CUDA branch. We usually CUDA is enabled on this branch. Not that it matters a whole lot. Let me see. I just ran with GraphBLAS 9.3 my test coverage. In process of that test coverage, it generates almost 20,000 kernels, and I've just done that. And there's a ton. I won't wipe them out because we might want to look at some of them. But I'll wipe them out probably and regenerate them. You can watch them get regenerated. And I also, every version of GraphBLAS has its own folder. So if I go from version 9.1 of GraphBLAS to 9.11, I create a new folder by default, so they don't conflict with each other. Okay, so let's look at the JIT, and let's look at how I do this decision. Okay, and I'll do it with the reduce again is the simplest, or one of the simpler kernels, reduction of a matrix to a scalar. So I'll kind of use that as an example. So let's start with the reduce and just imagine we don't have such a kernel. Okay. Now, if I go, I have a bunch of them compiled, I'm sure. Whoops. I got 20,000 of these puppies. Okay, there we go. I've got 239 reductions to scalars here.
Cool.
And so we'll look at
my
yep.
CX and my add are for a user defined type, I assume.
Yes, so that's a
Yeah.
complex plus.
Got it.
My add 32, I don't know what that is. It's in my test suite somewhere.
Right.
It's like, oh, fine. I don't know why I call it 32 because it's got 4 doubles. It's somewhere in my test. I have this.
Yeah, I got you.
It's a scalar with 4 doubles. And how do you add? Oh, well, why not just add all the 4 doubles? So that's the add operator. But that is a big difference. If you don't see this extra suffix, okay, these use only built-in types and operators. Well, mostly. Some of the kernels are type agnostic, like they're only constructing structural results. They don't care what the input type is. So I don't put that in the specification of a kernel. And so I could have the user-defined data type call that kernel will work just fine. So I don't specialize that. I take that
So
out of the encoding and the macrofying.
it'd be like pair or any.
Yeah,
I got
exactly,
you. Yeah.
exactly. And so, but for reduced to scalar, you're pretty much going to be dependent on the type. So that won't happen for reduce, but it could happen for matrix multiply. But so mostly these reductions will involve built-in data types, built-in operators, almost exclusively. But there's a few more. And I don't see any of my Gauss ones, so I haven't run my Gauss demo yet. If I ran my Gauss demo, you'd see some of those there as well. And you might see actually CUDA stuff. No, there's no CUDA stuff. I've got, oh, I don't have any CUDA kernels. That's funny. Okay. I thought I had CUDA enabled here. All right, well, maybe this isn't the version I've got tested. Okay, so so I'm gonna have to blitz those. So let's look at reduce to scalar. So we come in here with, say GRB matrix reduce. This eventually calls this method. So reduce to a C scalar. There's a whole bunch of these, and rather than type them all out, I made them a macro, so I could just put in, a template. And so I have all the built-in types, including complex type, built-in, the user-defined type. So they all use the common reduce to a, this is reduced to vector. This is reduced to a GRB scalar, which is slightly different. But that is just a wrapper around reduced to scalar. So the workhorse is reduced to a bare scalar without it. This is just a bare scalar. It's a GRBS, in this case, is a GRB scalar, but I just pass in the space itself where the value is and its type. So everything has to have a GRB type to it as well. It's a void pointer there, first thing. So GB reduced to scalar is the workhorse of all of these methods. It comes to reduce to a scalar. There's the scalar, that's the result. There's the type of the scalar, and there's the problem. And then I've got the workspace on a stack for small, little tiny things. Okay. So forget the CUDA. Say I come down for now. Let's focus on the JIT case for the CPU. Well, it doesn't much matter. They're practically identical anyway. So I'll come down and I'll say, oh, let's try to run this with my built-in kernels. And what if I don't have one? What if you've asked for a reduction and you want to do a double plus reduction on a float matrix? I have to typecast every entry. Well, then I don't have a kernel for that. So I will call, this will refuse to do it because the types then wouldn't match. Or maybe the switch case doesn't have that particular instance. Could be disabled. It could have, okay. And now I come to I decide, oh, well, I don't have a kernel for this yet. The result is no value. So I've not done it yet. So let's call everything that leads with JIT is the JIT wrapper, which I've explained already before. Reduced to scalar. Now that's not going to be here. Yeah, that method is not here. All the underscore JIT methods are in the JIT wrappers folder. And there it is, the reduced to scalar JIT. And these all you've seen this before. All these methods looks very similar. These input outputs are very specific to this reduction on the CPU, right? The CUDA reduced to scalar would look a little bit different, but they all have the same three parts. I get the encoding, which I explained last time, and then I get the kernel. So that's what I'm looking at today is how do we say, okay, let's get the kernel. If we've compiled already, it's in the hash table, just look it up. If it's not, I need to create it, compile it, load it in, and then call it. Okay. So it's the JITFire load thing. And this string is important. This is going to be the file name. This is going to be the name of, well, it's this word right there. Okay. And if it's a CUDA reduce, you'd see JIT CUDA reduce here instead of JIT reduce. These are probably dev2 branch. Okay, it's probably these kernels, because there's no CUDA, there's probably from a different branch. So I may have to recompile something as I'm going through here if we want to see more kernels. Or maybe I'll switch over. You know what? Let me switch over to the dev2 branch because then I don't have to recompile everything. That would probably be better. Let me just double check stuff here. Oh, I have CUDA. Oh, okay. So this is dev3. Okay. Okay, so how does the JIT guts of the JIT work? We're now in this rather large file called JITifyer.c. This has a bunch of methods in it. This is almost 2,700 lines of code. And I did this because there's some globals in here that only these methods get access to. Nobody outside this file gets access to these globals. And here's all these static globals here, static objects. Globals in general, of course, in a library are a bad thing, right? But I have to have them because I have to keep track of, permanent track of all this stuff, the hash table, the settings, like where do you keep all your cache? Where's the cache of all the compiled kernels and their source files? That's the string there. What's the name of the compiler? Because this could be changed. You can use grb get and set to change that with a global setting. There's lots of things I have to keep track of, and that are global objects. There's really no other way to do it because I don't have some sort of global context object in GraphBLAS where I can pass something around and all the globals will go inside there. I don't have such things. So these are globals, so it's a big file that then share all these. I'm very careful with globals. What I'll tend to do is if someone outside this file wants access to these, I don't allow that. And instead write an accessor method that says you want access to this global, you can only get it through calling this method that's in this file to get access to that global. So I protect my globals from GraphBLAS itself. Otherwise, I get myself confused. So these are a bunch of character strings that keep track of the state of the JIT, where how to compile it. But let's start with the entry point here, the JITifyer load, which is kind of it's not just loading, it's a bad name. I should change it. So what is this going to do? Well, the goal of this is to give me that function pointer to the JIT kernel I want to call. I may have to construct that, may have to compile it. It might be able to quickly look up in the hash table. That's the outcome. The input to this is, well, what family is this? In this case, it's the reduce family. This is an enum. There's only one kernel in the reduce family, or actually maybe two. The CUDA might be there too, I guess, the CUDA reduce. The name of the kernel name, the K name, I call it, and its hash, which I've already computed, This is the final hash for this kernel. It's now been computed by the encoding process. And also I pass in the entire encoding, which doesn't have the hash. The hash is a function of the encoding. I also pass in the suffix, if there is one, which is found by the encoding. When I encode it, I say, ooh, this is a add Gauss kernel, say. So I would need to, keep that add Gauss there as a string because I'm going to use that in the definition. And then I have these five or six things, which are, again, this is used for all JITs. And so, summaring, there's no summaring here. Well, okay, fine, it's null, right? The reduce doesn't use a summaring, so I just pass in null. It won't need it. Oh, but it's got a monoid. And then it's got, it doesn't have an operator. There's no operator. It has a monoid it's working on. There's no operator. Now you'll notice here, this is kind of funny, a GB operator. What the heck is that, right? Well, GraphBLAS has all these different operators, right? Unary, binary, index unary. What else? I guess that's the main ones. Those three. They're just all the same. Just to operate function pointer, whatever. Some types. I don't have three different types. Okay, well, I do have three different types because of the generic don't work otherwise. But they all map to, they're all laid out the identical, these structs to the GB operator. So like that op could be any op. It could be a unary op. It could be a binary op. In the future, it could be an index binary op. It could be whatever op I want to stick in there. And so I've got an operator potentially. So an EY's add. If I have an op that I need for the accumulator, I have a summaring and a monoid, I might need an accumulator at some point. That'll go there. And then I'll have three types. Now, whoops. Now, the JITs are only dependent on, at most, I determined three different types that are above and beyond the summaring and the monoid. Those are the three main matrices, the C matrix, the A matrix, and the B matrix. That's it. The mask matrix is not here. It's gone because I don't need to know its type anymore. Its type is already encoded here. All the built-in types are already encoded as well. And all the built-in operators are already encoded there too. I don't need these for built-ins because built-ins are already encoded. They're pneumified and encoded in the encoding. I have a fixed number of them that are built in, predefined, and I don't need the function point. I don't need to look them up. Well, I do anyway. I pass them in but a user-defined is all user-defined operators or types encode to the same number, but then they have to be specialized by their string or whatever. And so I have to pass in all these as well in the JITifier. So I'll use these things. So that's the input to this JITifier load. And as I said, this is a bad, probably it's not a very descriptive name as to what it's doing. It's doing more than just loading the JIT. It's compiling it, looking it up if it's already loaded. Okay. Quick returns here if you can't hash it. I have also a JIT control, which you can, there's 5 settings to the JIT. Where is it? It's going to be in, let me go to the JITifier.h. Okay. So oh wait, no, this is in GraphBLAS.h. There we go. Okay, there's 5 different settings for the JIT in increasing order of use of the JIT. Okay, on is the entire JIT. I can compile, load, and run. You can tell me, well, I don't want to do any compilation. But if you have a JIT on the file, a JIT kernel is already compiled, and you just want to load it in, like maybe you don't want to give the user application access to the compiler. Say, okay, don't compile anything. But if it's there already, just load it. It can also run previously loaded JIT kernels, not just the pre-JIT, but JIT kernels. Okay, JIT run says you can neither load nor compile. Just go with what you got. No file access. These controls are handy because if you have if you're running some set of operations which are not performance critical, but they're doing some crazy typecasting, they may compile a bunch of JITs you don't need because they're just going to be tiny. So just pause the JIT or just say JIT run. Just don't load anything. Don't try to compile anything. Just go with what you got. If you see something that you don't have, you might consider the JIT for, don't use the JIT, go to the generic kernel. And that'll actually be reasonably fast if it's for a small problem. So I give the user control over these 5 settings. Pause is different than off. Pause says, don't load, don't compile, don't load, don't even run any JIT kernels, but don't delete the ones you have. They're in memory already. Just leave them there, but don't even call them. That's a pause. Pause the JIT. And then off says everything is off. And DL close any JITs I've got. And also flag as unknown or untested any pre-JIT kernels that are baked into GraphBLAS. They're still in the hash table. Those are not removed from the from the hash table. But I need to check them the first time GraphBLAS touches them. And so let's pretend I've never seen anything. That's off. And that's like flush everything. So 5 controls. And then, so I come in here and there's a GRB get and set for this that changes this. And so if the JIT's off or paused, we're not touching any JIT kernels. So we fail. We pause. We don't do anything. So now we do the run case. Well, do I have it already? And this has to be fast. No critical section is accessed here as well. Critical sections is important because if I've got 2 user threads both touching the JIT, well, I need to let them into the JIT kernels as fast as they may be called the same JIT or different JITs. They need concurrent access as fast as possible. Okay, so I don't need critical sections for this case. And this is not just the run. I'm sorry, this is just the run case. Otherwise, yes, I'm sorry. If the JIT is in the run case, I can do this quickly. I'm sorry, I spoke too hastily. This is not less greater than equal to run. This is equal to the run case. In this case, I can just do a quick lookup if everybody's in the JIT run state. Because now that I know the hash table is not going to be changing on me. If the hash table is changing, then I have to lock it and do a critical section. So user threads both trying to access the JIT has to sometimes go through a critical section. If that's a problem of performance, before the user launches into their own parallel region, they can turn the JIT to JIT run. That means I know now the hash table won't be changing, and then they can use what the code I've highlighted here. That's why I have this here. A lot of concurrency issues here with the JIT that I have to worry about. So I'll just skip over this because the rest of the code will kind of do the same thing just inside the critical section. But just as a gist, I look it up in the hash table. If I've got it, great. If I found it, yay, and there's my function pointer, I'm done. If I don't find it, well, tough. I can't go any further because of the control is run. Okay. And then the rest I have to do in a critical section. So now 2 user threads will have to compile one at a time, or even just find the lookup one at a time. Because what if one does a lookup and the other one starts to, and they both want to compile it? I can't allow that. So So I do all this work now in a critical section, the rest of it. And what's happening here in my, okay, I guess I've gone past my typical style of 80 characters here. That's better. Okay. So this is now the worker. So what do I first do? I may have this already, in which case I just do a quick lookup. If I don't find it, I'm sorry, if I did find it, then I may have a condition where yes, I found it at this position, but I flagged this in the, where is this? I've flagged this as a kernel that's compiled. It's a pre-JIT kernel. It's compiled into GraphBLAS, but I've never used it before until now. And so now, since it's already loaded, I don't need to load it, but I look it up in the table. I get its query function, and I look at that query function, and as an example of a query function, I look to see say this one. Here's my own complex add function, you know, my own, I've got my own complex data type. Just as one of my tests, as I pretended to create my own complex data type. When this was created, it's possible that after this JIT was compiled, that definition could change, or this definition could change. So how do I check that? Well, that's why I have this in here twice. I have the C code and I re-inject it as a string. And then I can call this query function to say, cough up your strings, please. And so I can look at them to see if they're different than the ones I'm getting now. And if they mismatch, I delete this kernel, recompile it. That's why the query. And it could have been you compiled it in, but it was stale then. Right? I need to check that. So that's where this check is for the pre-JIT. And if it's bad, I can't close it. I just have to flag it as good. If it's bad, I have to remove it from the hash table that I built on GRB init time. Okay. There's two special cases for, I have to, let's see, what do I just have a special case for the user operator and user type, again, to see if it's changed. The same logic is going on here. So this is the case where I found it. Let me check to make sure it's okay. And if it's okay, I return it and return success. You have the function pointer, the DL function, and that gets returned, and it's good to use, go. And so this has to be fast, and it's pretty fast because I grab it from the hash table, I look it up in the hash table, I grab it. I very quickly decide I don't need to check it, it's already checked. Or I'm always paranoid about checking these two cases, so I always check those. Because these are JITs that compile a single function call to a single operator. Or this is something that compiles for a user-defined data type. There's no function pointer. What's the JIT for? Well, when you define a data type in GraphBLAS, in the spec, you just say, oh, it's 16 bytes. You don't give me the type. You just say, Tim, it's 16 bytes. Okay. I can't JIT that because I don't have the definition. What 16 bytes are you talking about? Okay, so give me the string. Give me double X, double Y, whatever, type def struct, blah, blah, blah. Give me the string. Now I can compile it. But in the spec, you must tell me the size as well. You might say, oh, it's a double X, double Y, so that would be 16 bytes. So you figure yourself, it's 16 bytes. That's fine if you're a C application calling GraphBLAS, because you can have the type def yourself. You can have this equivalent string. You can ask size of, pass it in, and I'm happy. I have the number of bytes which I need, and the string, which I need. I need both. Well, what if you're in Python and you can create a string that says type def struct double x double y. There's my type, please. And Python could say, well, I think it's 16 bytes, but let's ask the C compiler. Well, that's a pain in the neck. Python doesn't want to talk to the C compiler. Let me do that. So I construct a JIT whose sole purpose is to return size of the type. That's all it does. So you indicate that in GraphBLAS, in SuiteSparse GraphBLAS, by giving me a size of 0. If you give me a size of 0, that tells me you have no clue, and then I'll compile a JIT kernel to find out how big it is. So those are those two families. The same thing is true for a user-defined operator. What if you don't want to give me the C function pointer? You can create from, say, inside Python, you can create the string itself for the function. You might be able to just have a definition of the string sitting there. Do you want to go compile that? Probably not. So don't, just give me the string and give me null for the function pointer. Fine, I'll compile the function itself myself. Now, I won't use this in any other JIT kernels, but I will use it in a few special cases where I just want to call the function once or twice or log n times. Because why call a JIT, why construct a JIT kernel to do something trivial like that? Just call the function itself a few times and I'm done. Then I need a JIT for that, for the function pointer. So that's what these two families are. Okay, so I found it, great. That part has to be very fast. A quick lookup. And so yes, this is inside a critical section, say 2 user threads, but it's just a hash lookup. It's locked the hash table, go in, grab it, come out. And if there's no compilation, that's going to be very fast and it won't cause a lot of collisions or conflict over that critical section. It's just a quick, I won't bother to look into the code here. It's just a quick hash table lookup for that hash. Give me with a given encoding and given suffix, go look for it, and there it is. And I also return, if need be, the position in that table. And so I can return, this extra test to say, oh, there it is. If I find it, let me go double check it. That's its position in my hash table. And then also return a flag that says, oh, this is a pre-JIT kernel. And that's the index in this table of its pre-JIT kernel, because I have a table of them. It's not in a hash table. It's in it's in this list of kernels and their query functions. It's pre-compiled. It's not in the hash table for the pre-JIT. So I can very quickly query it if it hasn't been checked before. So it's in the hash table, but I have to check it. I don't add it until I check it. I could have done it that way, but I didn't. For pre-JITs, I put them all in the hash table at the very beginning. Okay. So now, whoops, I don't have it. Or if I have it, I don't like it. I queried it and I said, hey, your types have changed. So I now have not returned success. This means I'm falling through to this case to say, I have to go and load the thing. It's not in the hash table, or if it is, it's bad. Let me go. And if it's bad, I've freed it. It's just not in the hash table. Let's see. No, this is a pre-JIT I'm querying. Sorry. If it's a JIT kernel, I find it, I assume it's good. I don't check it every time. It's too costly to do that. So it's not in the hash table, basically, or if it was a pre-JIT in the hash table, but I disabled it because it's changed. Now I say, okay, I've got to go load it from disk. I may have to compile it. So I may have to compile, I may have to load it. Oh, but wait, if the JIT control is less than equal to run, you can't load your whoops, what happened to my here you can't. I have to load and or compile a kernel now. If the JIT control says you can't do that, well then there's no JIT kernel, go away. All right, so now we start to go into the process of potentially just loading the JIT kernel from a file. I got to find the file name, and then I'll check it when I load it. I'll query it to make sure it's still good. It's no longer a pre-JIT because pre-JITs are already baked in. They're not loaded from a file. Or I have to compile the kernel and then load it in and also check it as then as well. Okay, so how do I do this? Well, the family determines this family doesn't determine very much. It's slightly different with the user-defined operators and user-defined types, how I check those. And it also affects, where is it else? This switch case. How many digits do I need to encode this in the file name? If you look at these file names, this is the reduced kernel 03F1. That is 1, 2, 3. That's 7 hex digits. Okay, that's because that number 7 right there. I only need 7 hex digits to encode all possible reductions. But matrix multiply, it's like 62 bits. I'm almost out of bits. So it's 16 digits. And so it'll affect the length of the file name and the function name. But then these families also are going to grab certain operators, like multiply will have 2 operators. It'll grab this one. This one needs to grab the monoid from the semmering, and so on. So these are just instances, like a sign has 12 digits and it only has 1 operator. It has no semmering, no monoid. Reduce has the monoid, but now I need to get its operator in op1. And so now I have all the components of the family. I think this is the only thing that depends on the family. Now we start the macrofication process, even just to load the thing from disk, because I got into the file name. So the macrofying is the process of all these macrofy methods here. It's the process of creating the strings that go along or define a particular JIT kernel, or the name of the file, or the name of the kernel, which is the same thing. And here, for instance, macrofy name is going to produce this file name right here, JIT reduce, blah, blah, blah. Actually, I put it also at the top. Is now, if it's not in memory, I got to load that file name, .so or whatever, .dylib if I'm the Mac, or .dll if I'm on Windows. So that's the thing I'm now looking for, but I got to produce that name. How do I produce that name? Well, it's always starts with gbjit underscore, all the JIT kernels, gbjit double underscore. You notice I have double underscores here because I have regions in this name that I need to split apart carefully. The name of the kernel name, which could have an underscore in it. So I put 2 double underscores here to delineate that. And actually, if there's a double underscore, no, I control the names. Nobody has the names. So my names never have a double underscore in them. So that, I think what I do when you define a user-defined operator, if I see a double underscore in the user-defined operator, I think I've forbid that. Because otherwise it gets my JIT confused. I might not have to do that. I forget. I can't recall. Okay, so I can split this. I can parse the name. I can go back and forth between the name and its components easily. And it's going to have the name of the kernel. It's going to have its encoding, which is not the hash, which is that encodify outcome, which in this case is like for reduce, it's 7 hex digits. And I use hex because then I can look for the bits easier. Okay, so I need to first get this name of this file to see if I have it already. So the first macrofy we hit is the macrofy name. Okay, so this is just a sprintf. I have the kernel name, which is a const car. It's a car space I'm writing to. I've already allocated it. It's just sitting right here. I need to construct this kernel name. It's just a sprintf. It's going to look either like this or this. So it either, if there's no suffix, it looks like this. And so it has the namespace, which is gbjit. I think they're always gbjit. I think the namespace has, I think for CUDA, I was going to have a different namespace for CUDA, but I didn't end up needing to do that. So the namespace is always gbjit. I don't think I macrofy name in any other way. Let me see here. Yeah, the namespace is always gbjit. I was gonna have a GB CUDA for different namespace, but I ended up putting that in the kernel name anyway. It was simpler. So I get the name of this kernel. And now I need to lock the kernel. Because what happens now, it's already inside a critical section. What am I locking for? Well, wait a minute. A critical section only protects between two user threads in the same application. What if you're running two different applications? I'm paranoid. Right? What if you have two different applications that are both calling GraphBLAS and they both want to compile the same JIT kernel at the same time? That's just going to be a mess. So I have a file locking mechanism where I'll create just a file that's only for locking with, but this name of this file is based upon this instance of the kernel name. Where is it? Let's see. This is oh, it's only dependent on the hash function, I guess. I figure if there's a hash collision, you know, then two kernels might be different, but they'll just lock the same hash. So fine, they'll have to wait on each other. So that's going to be an unlikely hash collision. So I lock the file to make sure. And if I can't lock it, this is probably overkill. I don't have a retry process. Let's try again. I say, ooh, I can't lock the file. What happened? Well, I just turn off the JIT. It's probably overkill. It's a fix me here. This is too pessimistic, but that's what I do. Then finally, now I'm going to go and try to load and if it's not there, I'll compile it. That's what this load worker function is doing. So now I'm going to load and or compile the kernel. Again, I have all the same things, except now I've pulled out some ops that I need because of the family. Otherwise, this is the same. So now I'm going to try to load first. I construct the file name and I try to DL open it. And I say, oops. I say, oh, great, I got it. I loaded it into memory. Yay, I have it. Well, now wait a minute. I've just freshly loaded it. It could be a week old. I could have stale bread here. So I query it. I call the query function that kernel, and I get the function pointer for the query function with this name. It's always called gbjit query. They're all called the same. And then I call it. And I say, hey, are you the kernel I think you are? And if it's not, I close it. I delete the file. And now I pretend as if, where is it? DL handle, where is DL handle? Yeah, DL handle now is null. I don't have it. I pretend I didn't have it. Like you never saw this. It's now deleted from disk. It's DL closed. There's no DL handle. Now I don't have it. So I never had in the first place. I looked on disk and it wasn't there. Or I looked on disk and it was bad. Now I'm coming to here. We haven't got to the macrocation yet, except for the name. Okay, now I have to compile it. I have to touch the compiler. Oh, well, I better have full compile control to do that. So if you don't let me compile, I can't compile. No, there's no JIT. Go away. Okay, so now we have to create the kernel, finally. And this is one of the very simple decisions if it's CUDA or not. All the kernels have an enum. So here's all I've got currently a list of all my JIT kernels. Like we're in kernel 1, JIT kernel reduce. I've got 44 kernels that are active. I've got about 40 more that are planned, but for the future, I don't have yet, up to kernel 87. That's 43 more. And then I've got CUDA kernels starting at, well, CUDA kernel 1000 is not a kernel, it's just a placeholder. These are all my CUDA kernels. Okay. And they start at 1000. So that just determines the kernel code then is just in one space. It's just a kernel code. There's no, otherwise no difference between CUDA or not CUDA, but this is bigger than 1000. And so that just tells me the file type. Are you a kernel CUDA? So now I create the file name in this temp string space, create the file name. I'm going to write the source file. Okay. So how do I write the source file? Well, it's several processes right here. This whole process is going to write the entire JIT, both CUDA, all the JIT source, it's right there, everything. It's going to construct the preface. It's going to macrofy the whole family. It's going to print the switch to say, are you a JIT or a pre-JIT? And I'll macrofy the query function and close the file. This produces the entire, and so now this will do all macrofication all the way down. All those macro methods will be touched here. So let me just dive into that. So you can see so far that the CUDA specific stuff is very limited. Here, the type of the file name extension .c .cu. The preface is going to be slightly different. What is the preface? The preface is not in this method. The preface is, you may have a user-defined data type or user-defined operator that needs, say, pound include math.h. Well, that's already there. Pound include, I don't know, some library that I don't know about. You may have to tell me, or some definitions that you need to give me. You can give me in the JIT preface if you wish. So that's what this produces, and it also produces these nice little pretty comments right here. I think it might produce all of that right there. So the preface, let's just walk through the JITifier, the macros one at a time. The macro preface only depends, macrofy preface only depends, this is the comments now, it only depends upon the kernel code, I think. And that is only needed to know, are you CUDA or not? And if you're CUDA, I just do pound define CUDA kernel. So I can have later on, I can have if-def CUDA kernel. If I have anything in my user-defined function, and I need to make this documented for the end user, like this should be GXB CUDA kernel perhaps, where I can tell the user, if you want to construct a user-defined operator that's different on CUDA than it is on the CPU, then you can if-def it with this if-def. And this if-def also impacts the decisions made inside the include file here, because I have pound includes like, CUDA.h and that sort of thing for the JIT kernel, which will be included only if it's a CUDA kernel. But I just put in comments here, version number, like this was done for GraphBLAS 9.3. So you can look at that file and say, okay, this is a 9.3.0 kernel. And I better not use it for something else, another version of GraphBLAS. And so that's just some comments so you can just more easily track these files. So there's the preface, very simple decisions to make there. Now this is the guts of this is going to produce the most of the definitions for a given kernel. Macrofy family. So this does depend on the family. Are you a reduced family, MXM family, and so forth? Big switch case here, and that's it. That's all it is. It's just a gateway into all the other macrofications. So macrofy reduce will come here. So the reduce family will call macrofy reduce now. And all of these have a bunch of operators, a bunch of types. Well, fine, I just pass them all down again. So some of them aren't used. Apply doesn't have the semmering. Right, the only thing that has a semmering is the MXM family. Nobody has the monoid except the reduce family. Because the semmering uses a monoid, but it's inside the semmering. I don't need to have it separate. So macrofy reduce. And what is macrofy reduce given? Well, it's given its encoding. That's a 7 hex digit thing, if you will, or how many 28 bits, whatever many bits it is. For MXM, it's 62 bits. This is a component of the encoding. It's the encoding code. The encoding is a struct that's got other stuff in it. I've pulled that out now. I'm passing in just this. And it's got the file. I'm going to write. All these jobs of all these macros methods is to write to a file. This file right here. Okay, stop me if there's anything that's not clear.
Oh, I'm following along.
Okay, cool.
Yeah, it's making sense.
So macrofy reduce. Or I'm going too slow. Maybe I'm going too slow. Macrofy reduce. So what do I got to do? I've got to decode that encoding. I've got to unpack, well, what the heck is this? This is an O3F1 kernel. Okay, what does that mean? Okay, let me pull out those terms. So this is doing some bit shifts, and these are the size of those bit fields. For instance, 2 bits defines the sparsity. 1 bit defines whether you have zombies or not. 4 bits defines the type, because there's 14, 13 types. So I need 4 bits for that. Okay. So now I'm going to start to produce this. So the first thing I need to do is just add a comment, just so I can look at the file to say, who the heck are you? Oh, you're a reduced kernel, and you're doing this operator with that data type. So that's what this produces. It's part of the monoid, and the data type is the monoid type name. Okay. Now I have to macrofy any type defs, which I think is this one. Yeah, just this one. Some macrofies, the macrofy reduce has one data type it's working on. The Z type of the monoid. I never have to do 2 because, oh, you think, well, the monoid has its own data type and the matrix has its own data type. Those are 2 types. Tim, don't you need 2 types? No, well, yes, there are possibly 2 types and there's possibly typecasting between them. But I only need to know of 1 type because if it's a if it's a built-in type, I don't need the type def. It's built in. I only need to do a type def if it's user defined. And if it's user defined, no typecasting is allowed. So these 2 types must match. If you have a reduction over a user defined type and the input matrix isn't that type, then yeah, I can't do it. There's no typecasting permitted between built-in to user defined or between any 2 user defined types that are different. So there's only 1 type def I could possibly produce. So this macrofy type defs, it only has 1 type def to do. So macrofy type def is going to macrofy a bunch of types. I don't call it type def singular. It's type defs because I'm going to do a bunch of them, possibly 6. I never need 6, I think. But potentially there's 6 data types here. I just don't know which 6. Some of them are going to be potentially user defined. Not all of them can be, because you can't cast between user defined and not. But so fine, I could have up to 6 types. Probably 3 would be more. Anyway, but I just don't. I just put all 6 in just to make it simple. 3 matrices and the X, Y, and Z types, I call them. Those 6 letters are important, by the way. CAB, a C always refers to the output C matrix. A and B always refer to the 2 input matrices. X, Y, and Z, though, are for the operator. Say, for summary, it's the multiplicative operator. The Z type is always what the monoid works on. It's always Z to Z to Z. The monoid never goes outside its own domain. And then once you finish the monoid, you cast it to the C type if necessary, out as the output. The mask is not here because the mask can't be built in. I'm sorry, you cannot have a mask. Well, you can have a mask that's a built-in type. I'm sorry, you may have a mask matrix that is a user-defined type. That is possible. But if you do that, it cannot be a valued mask. You can't tell GraphBLAS to look, because that would require a cast to Boolean, and you can't cast from user-defined to Boolean, not permitted. As a result, the mask type is already purely encoded as built-in, or it's structural, which is also a built-in flag that says, hey, it's structural. Forget the type. We're not looking at the type of the mask matrix. And so the mask properties, the type of the mask, if it's valued, is just built in. So it's in the encoding already. I don't need to do a type def for it. So it's not in this list. I pass this in as a single method because I'm going to iterate through those methods, and I want to make sure I don't duplicate the type def. Because if I had 3 types and they're all the same, I'd have type def, type def. Well, that's a compilation error. You can't type def something twice if it's the same type def. So I just make sure that it's only do the unique ones in this list of 6. So that's what you see here. Okay, to type def a okay, and I do this. So where is the output? So here's an important notion now. This type def is going to appear twice. The first time, I'm going to stick in the string and directly, and that's this one. That when you gave me the string, I print the string. Is it a valid string, valid type def? I have no idea. I'm just stick it there. If it doesn't compile, it doesn't compile. That's your job. Right? I'm not a compiler. I'm an operating system. The GraphBLAS OS. That's what I feel like sometimes. Oh my gosh. Right? I mean, gosh, I've got file locking and hashing of directories and loading and open deal sims, and oh my goodness. I feel like I'm calling out to a compiler. I feel like I'm an operating system.
About halfway there.
Yeah. Multiple processes, locking, critical sections, blah. Okay. So that goes there. But I want to repeat the thing as a string. So I want to produce this. And the reason I want to produce is a string, and so I can stick it down here. You see, so the type def is in there as a pure C line of code, and the type def is also there as a string, so this method can return it to its query caller. Query the library is like, who are you? What's your function? Oh, here's my source code, my type def. Or here's the definition of my user function. My CX plus is this. Okay, so that's why I have this printing twice. One as it raw and one as I have to have the name, which is GB, which is like my CX there, and then the string itself. So that's a simple method. I won't show you what that looks like. It doesn't much matter. So the type def's there. Now you see, I'm gluing together a lot. So I'm going to reuse this method in a lot of other Macrophise family methods. Like they're all going to have different sets of type defs. Well, here, this only has 1 type. Oh, 2 types, actually, which is probably overkill. I could have gotten away with 1, I guess. But I'll check if there's no typecast. I don't know. I put in there twice. I have both the type of the matrix. If I have to macrofy the type def and the Z type of the monoid. One thing, let me go back to this. If a method, if there's no type, it's null. But if the definition inside every type is a string with its definition, Oh, int64. I don't need the string for that. I know it's a grb int64 is int64 underscore t. You see, I don't need to type def that. I don't need to have a string for that definition anywhere. And so this is an empty string or a null pointer actually. So it's that there's a check for null here because if it's a built-in, this type might be here, but if it's built in, this string is a null string. And so it's just gonna be skipped over. So this only has to do the type test for user-defined types or operators. This is doing, or no, this is user-defined types, sorry, not operators. But they have to be unique. Okay. So now I need to construct everything having to do with a monoid, but this is just macrofy monoid because this simmering is going to have to call this too. Because the simmer has to macrofy a binary out for the multiplier. It'll also have to macrofy its monoid. So this is its own method. I first though have to give this, I want to have a, so now get into the meat of the macros. So these are the macros that all my template methods are going to use to know how to be specialized. So I'll have, for example, if you look for A to Z type, okay, there's two of them here. So a monoid reduction via monoid, there's two types to deal with, the Z type of the monoid and the A type of the matrix. And they could be different. For user-defined types, they can't be. But they're both, so I have a macro, rather than in C++, you have the template parameter, you put the type in there, blah, 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 I can't do that. So it's pound define, the GBZ type is this, and then GBA type is that. Whenever I need to declare a variable, I use that type. And so so this is what this is creating right here. I need to first define, hey, the Z type is called myCX. Everybody else knows now below that that's the name. And now I could have, okay, so I could have had a guard here. With the type defs, I look for uniqueness. I wouldn't actually have to do that if I use these guards. I started to try to do this. I didn't like the guards. It's kind of ugly. There's an if-def guard here. Do you see this between here? No, that is end if here. Here, this. We're not there yet, actually. We're jumping ahead. But this one line of the type is produced here. Now I'm going to macrofy the monoid. Okay. And then I have other macros down here that's going to produce things that are specific to reduction to scalar that I'll use in my template codes for that. So how do I macrofy monoid? Let's look at macrofy monoid. It got a little bit, I'm using a guard here in here because what if you have a plus plus semiring, say? Your monoid and your multiplicative operator are the same operator. Oh, whoops. I can't define them twice. I got kind of like I could produce these in different places, and then there's another operator, say these accumulator. We could have three operators floating around. Like, do I have to do those string comparisons to make sure they're all unique? I kind of gave because I was producing them in different parts of the code. Like, fine, I'll just spit out the code, but I'll put in a unique guard, but it's unique to the name of that function, which has to be naming that function. And so this is the name of that function. And if it's already defined, if it happens to appear later on twice, well, this guard will say, hey, it's already defined. If not defined, define it, and then end if down here, right? So there's a guard like a pragma once in C++, right? It's only defining it once. If it appears again, that whole body of code here will appear again if it's used again, but then it'll be not seen by the compiler. So Macrofying a monoid, what do I have to do? Well, the monoid is defined by a whole ton of things. It's, well, the monoid itself. That's could be all I would need, but I have more things to it. I have a, I've already encoded this monoid. It's in the bits already. And I'm going to use those bits, I've extracted those bits out. I've got an add operator as an enum. I've got the identity value as an enum. I've got the terminal value as an enum. I have a Boolean if the output matrix is ISO or not. I've got the monoid itself. I could find all these things from that if I like. I also have a special case for this matrix multiply where a monoid can be what I call terminal. It basically means like a short circuit, like logical and stops if you see a false, right? There's monoids that have, or I call those terminal monoids. They have a terminal value that if you reach them, you'll never change. Plus is non-terminal.
Like
Plus
zero to multiply, zero would terminate multiply.
Yes, if it's an integer multiply, yes.
Yeah.
Not if it's floating point.
Right.
Because technically the terminal value for floating point is nan.
Yeah.
0 times nan is not 0, it's nan. So yeah, times would terminate on a 0, for instance. Okay, but some cases, so I have terminal condition codes that I'll check here. Where is this? Where's the terminal condition? I guess it's not in here. Is terminal. I thought I would produce it. Oh, I thought I would see it. Okay. Because reduction can be terminal to scalar, but I don't see the terminal condition here. I guess I don't even produce it. I think I have a if def, like if def is terminal or something. I could look that up. I forget how I do that at the moment. Anyway, so what do I have to do to define the monoid? It's all of this down to here. This I have to produce. So what do I have to produce here? I have to first define the binary operator. That's this. And down, that's going to produce stuff all the way down, actually to here. It's also, this function's also going to produce those two operators. I have a macro called add that's going to do the add. How do I do the add? Well, if it's calling a function, there's a calling a function. If it's z plus equals y or something, I would put in the string z plus equals y. You'll see that in a minute. I have to macrofy the binary operator. So this is a big beast because there's a lot of built-in operators. And so in the encoding, every built-in operator had its own unique encoding, its own enum, if you will. And user-defined ops are special. They're like 0. They all code to code 0. This is a code 0 because it's user-defined. Okay. If the output is ISO, there's no operator needed. So I just do nothing here. It wouldn't happen for the reduced to scalar. If it's ISO valued, if the output is one number that's always going to be that number, then I don't even call this JIT kernel. So this is for the for say MXM case. You're doing a matrix multiply. If I know that the output matrix is ISO valued, all the entries in that are present in the matrix will be equal to 3. Well, then the JIT kernel is not going to produce those numbers, 3. I'm going to produce that outside of the JIT. And the job of the JIT is just to do the structural computation. So how do you update something? Well, it's an empty macro. It's going to disappear. This add or this update for the monoid is just going to disappear right here. There's nothing to do. Okay, but the reduce is not going to touch this. So the first thing I do is, well, hey, this is user defined. Okay, if it's user defined, I spit out this definition. I won't maybe go into that detail. It's a simple method. And then I have to define the macro, these different macros. I can pass in the name. So this is the add macro I'm producing. One thing, and this is because you see in GraphBLAS, SuiteSparse GraphBLAS, I have positional binary operators already. You just can't define them as user can't define any, but I have some built-in ones. So I have to potentially pass in the indices to this function. Now here I don't. It's for a monoid. Monoids can't be positional, so they're just going to be a function of x, y, and z. That's x, y, and z are the arguments here. But a binary operator that's not a monoid will be defined with the indices as inputs as well to this macro. However, I may have to flip it. And I should use a different word than flip xy. Flip xy. Oh, I'm flipping x and y. This argument for k may have to be different too. Hang on. Oh yeah, flip xy also flips the indices. So what does flip xy mean? Suppose I'm doing a times b. I'm not here. That's not happening for reduce. But the submarine is going to use this code as well. I may decide to do B transpose A transpose quantity transpose instead. I may decide to say, hey, wait, let me just reverse this around. And when can this happen? This is collapsing cases together because you've got matrices stored by row or by column. You've got descriptors that are transposing or not. And that's 4 different cases for any given matrix. Well, that collapses to 2 cases. It either goes this way or this way. And so in that process of morphing these around, I may decide, oh, wait, I don't have that. I'm going to do this instead or something. I may choose to multiply instead of A times B, I might choose to do B transpose times A transpose. Great, that works. It's linear algebra, right? Yeah, it works. But wait a minute. What if the multiplicative operator is not commutative? Oh, okay. Then I have to eventually reverse those operands so that the B matrix has to go to the first input of the operator and the Y has to go to the second one, not the other way around. So that's what has to happen here, if this is true. Here, it didn't happen. And it's a monoid anyway, it doesn't matter. Monoids are always commutative, so I don't have to worry about it by definition.
So you're kind of hiding the collapse from the operator.
Yeah, I'm faking it through the macro.
Yeah, I got you.
So if this was, say, a multiplicative operator, but it had to be flipped, what you would see here is a yx and then xy. So I don't have to change the string, which is a beast. You'll see down below. I just flip it in the macro definition. And it works.
Yeah.
See, that's cool, I thought. Because, and then if it's a monoid, I also want to have an update macro, which doesn't add to its from Z to itself to simplify. So that's the user defined. If it's a built-in operator, I just want to produce these 2 strings. Okay. And I want to produce, so let's look at a simpler case. I don't know, let's just grab one at random to see what we find. This is a reduction plus. Oh, perfect. Okay. This whole macrofy monoid will produce those 3 lines of code. No, this macrofy binop will produce these 2 lines of code. There's the add function, and there's the update method. And so the plus, that's going to come down and produce, let's see, let's look for plus equals. That'll be code 11. There we go. plus, but it's only plus for the real case or integers, because plus complex has to be a different code because of Microsoft. If it wasn't for Microsoft, there would just be one case there. But Microsoft has to have a function or macro or something to do add to floating point double float complex numbers together. It's a piece of garbage. It's a Microsoft CL compiler, right? So the plus complex case is a built-in operator, and it has to be that function. And there is no update. If there's no update, then the update is just to do the add ZZY, like you saw before. So in this case here, I just got rid of it. Let me look at it again. This one here, there's no update function. I just have to call the plus function with a Z operand as for X. So that's what, so it'd be a null for this string up here. Or it wouldn't produce it. It would just produce an empty, where is it? The update. Yeah, the update is just the previous macro itself, the ZZY right there. But this one, I have two strings to spit out. So for plus, those are the two strings. So basically, this is a big, huge switch table that I don't see. This is the macro file. It only has to happen once when I'm running the file. So this can be kind of slow because I'm going to compile this code anyway. So every operator has a code, and there are up to 139 different built-in strings currently. So that's bigger than 2 to the 7, less than 2 to the 8. So the E code is 8 bits. If I have an operator, I need 8 bits to encode that operator. And I've got all the operators: first, second, any, why not? Just be it. Min, I have 3 different kinds of min: float, double, and integer. I have potentially 3 different strings. And the reason there is that the first string is the basic expression for the binary operator. It's a string that defines how do you mean to do z equals f of xy. The use string says what's the update string, but the update on the CPU, because the GPU might be different, and that's the G string. So I am going to, it sounds like a guitar, right? The G string. It is going to then potentially be a different string. And if it's null, it means it's the same as the update string. It's the same. So for plus, it's the same. On CUDA, it'd be the same. But in some cases, so for say min integer, okay, I guess I decided to use the ternary on CUDA, but if I'm on the CPU, I do the if test for integer min. I decided this was a little bit faster, but I decided this is faster on CUDA because CUDA doesn't like branches, ifs. CUDA doesn't like ifs. It doesn't mind ternaries as much as ifs. I don't know. You'd think the compilers wouldn't care between those two, right? But this is just a matter of tweaking the code and optimizing and realizing, oh, look, on the CPU, that's faster. On the GPU, that's faster. So fine, code it in. So I have possibly 3 strings. And I'll produce, if I looked at the CUDA kernel for this string would be different if it's a CUDA kernel. So these are all my operators: times, exclusive or, and, bitwise and so forth, all the way down. Okay. The first 31 E codes are permissible for a monoid. That means when I encode the operator for a monoid, I know that it's going to get an E code of no more than 5 bits. But I may still preserve 8. I'm not sure in the encoding. I'm running a compiler here, basically. And then I have all, basically, you name the operator, built-in operator. I have my own function call for do integer division. Oh, this is why it was rather difficult to have. I had too many macros, too many definitions of strings lying around. So I just put a guard on them because I might have to repeat them multiple times. Integer division or typecasting is also, I have to create a function. I have a function to typecast. This is not, here's a unary operator, typecasting is. There's some typecastings, you don't see it here because this is a binary op macrofication. I don't just type, I can typecast int to double, that's safe with paren int, or int 32, double function, output int, great, works great. ANSI C compiler says, fine, I'm happy with its result. Typecasting a double, no, I got that backwards. I'm sorry. Typecasting an integer to a double, that's safe. The compiler does the right thing. Typecasting a double to an integer, I can't trust the ANSI C typecast because I don't like it. The same is true here. I can't trust integer division from the compiler. I can't do x divided by y if x and y are integers. I never do that, unfortunately. The reason is divide by 0. If you happen to divide by 0, integer division by 0, what do you get? Well, you don't get a NaN, you don't get infinity, like int 32 max, int 64 max. You don't get undefined number, which would be better. Your program dies. You get an abort.
Yeah, it throws a signal. Yeah.
Like, oh my gosh, you got to be kidding me. That's the undefined behavior that ANSI C says. It's undefined, so let's abort. I don't do that. I do the MATLAB thing, which 0 divided by 0 is NaN, integer NaN. What's integer NaN? Well, for a long time, people didn't think 0 was a number. So that's a pretty good candidate for a NaN.
Yeah.
So it's 0. The integer divided by 0 is 0. Because that's the closest thing to a NaN I can think of.
And obviously the reason there is that you're just doing so many divisions. Like you're gonna abort in the middle of some
Oh my
matrix
gosh.
somewhere. Yeah.
Yeah, like if you have a plus div centering that's integer and you're dividing by stuff, like what happens if I ever divide by 0? It could happen. And in my tests, it would happening. Oh, and it would crash my whole test. It's like, I don't want the user to see that. I don't want to see that. So I do the MATLAB thing. I define it. I say, fine, integer 0 divided by integer 0 is a 0. Integer non-zero divided by 0 is, say, plus or minus infinity. What's infinity? Oh, if it's 32 bits, integers, like signed integer, it's int 32 max or int 32 min. Why not? That's the closest to infinity as you can get. So 1 over 0 is if it's integer 32, is int 32 max. Why not? The alternative is abort. I know.
Yeah, that's no good.
So that's no good. So I have to have, and the same thing here, stupidity for Microsoft, I have to define complex division. Complex float double div is fine. I also have to do reverse division because division, my built-in operators are in GraphBLAS. I added some, and here's why. I looked at the operators and I had this idea of, reversing operators around, right? And so I could say A times B, no, B transpose A times, just use a different operator. Use the operator that's, oh, it's it's commutative. Oh, then use a plus, it doesn't matter. Oh, but what if it's divide? Oh, dang it, I don't have a, well, and X over Y is in the spec. Y over X is not. So I added it because then I could just say, instead of using the divide operator and forcing it to be flipped, I just renamed the operator. So what I have now in GraphBLAS is all the operators, like first and second, are not commutative. But if you take first and reverse it, you get second. Take second, you get first. So all of my operators in GraphBLAS that are built in are either, I either know them to be commutative or they have a peer that is. Like divide, reverse division, RDiv. So I put it in the RDiv as a result. Maybe now I wouldn't have had to do this, but it just made life simpler to do that. So I only have to worry about flipping user-defined operators then as a result. I can just rename them if they're built-ins. So this is the reverse division y divided by x. Greater than, less than, Boolean, bitwise operations, bit sets, and so forth. Yeah, I don't know, power. I have to be careful about how I call power, because what do I do? Oh, the infin NAND behavior was weird and it wasn't matching my MATLAB results. So I have my own power function. I call power F or POW. Okay, but yeah, I check for NANDs and IMPs first. So I get the same result as MATLAB. All the sines and cosine. Oh, no, sine and cosine are unary. These are, atan2 is a binary operator. These are, I tossed in all the math methods I tossed in. And then I have my positional operators. These are built in now. They've been here for a while, long time. You just can't define your own. I have to extend this to make them user definable with the index binary op. Yeah, there's your indices. Stick them in. Okay, then I create the kernel, and if I have a G string, that means the GPU wants a different string than CPU. So then I use my ifdef CUDA. I'll put in either, I say the update is either the G or the U. If you're CUDA, it's G. If you're otherwise, it's U. Now I could have passed in the fact that, oh, this is a CUDA kernel you're sticking in. So just put it in the right string. I didn't do that. I just wanted to make it, I don't know. I just did the ifdef, just this. So I don't have to pass that in, I guess. I don't know, because I know what I'm compiling at this point. I could have passed in the flag that says, hey, you're writing a CUDA kernel. And then I could have just put in the G case for GPU, not the update string for U for the and if I do, otherwise, if I have a U string, then I'd say it's Z plus equals Y. And if I don't, I just have to call the add macro like I did for the user defined case. So that's it. And then I return this to the caller, and there's my binary operator. And I don't actually then, yeah, I think I use these expressions later on. No, I don't. Oh, I pass them as output to the macrofy mono. I forget what I use them for. Okay, so I'm still macrofying the monoid. I've only gotten to here, right? This is the entire macrofy monoid. It has to produce all of this. And I basically have to go through now and produce all the, like, oh, here's identity value. Here's how to define a const identity value. Do you have an identity byte? So I can do memsets. Yes or no. Memset, just set a bunch of bytes. Say all the bytes to 0. If so, there's the 0. Or could be FF or something, all ones or something. Memset can be faster if it's a big scalar than defining a large type. This is, let me look at the user defined one. This one does. Okay, this is a monoid that's a plus monoid of complex. So yeah, it has an identity byte. I could declare an identity value this way, but it's just with a memset then. This is the macro that says declare a scalar and initialize it to the identity value of the monoid there. See, with a user-defined data type, I don't know that it's zero, a double zero and a double zero. You just give me the bytes, you, the GraphBLAS caller. When you define a monoid, you define the identity value as a pile of bytes. So I just stuff those bytes in there. I don't even have, I mean, no, it's the Z type. I know the type. So there, it's the Z type, but I just have the bytes. Well, I can look across those bytes to say, oh, they're all the same byte. There's 16 of them. So I can use a memset here to initialize that. And this also tells me I can do the same later on if I want to. I also put in the size of my data types, 16, size of my CX is 16. So I can so if I need to, I mean, the C compiler would be happy with size of my CX, that would also work. But macros with an expression like that might compile differently than if it's just hard-coded 16, because I know the size of the type already. And this tells me how many bits it is. And I think I only use that for CUDA, how many bits the type is. And that's what all this logic does. Ton of different cases. I even have a very special case only for built-in operators. So it's not, I have the opcode. I have the whole operator. Okay. I produced the pragma for an OpenMD SIMD reduction. And that's this. For 3 or 4 different monoids. Types, sorry. Monoids, yeah. Times exclusive OR, bitwise exclusive OR, and plus. You can do an OMP SIMD reduction on that type of Z. And so if there's ever a case where I can do a fast SIMD pragma, I can stick it in, I can stick that in. And if it's not defined, I don't, if and def, right? And it's not defined, and I don't put it in the macro. I define it as the empty string later on. So there's various like special cases of monoids that I'll define that tell my kernels to do special things with these monoids. I put those things in there too. So yeah, it gets crazy. Oh, this. Let's look at this one. Okay. The user-defined type didn't have that, but this one, this is a known, it's an int 64 plus reduction. Okay, the monoid is plus and of type int 64. Okay, what does that mean? Well, it means I know at compile time that I can do this update with an atomic OpenMP. That's useful to know. And I can also, and I define that it has OpenMP atomic update. And it also has a CUDA built in that works for it as well. And there's the method to do the CUDA. This is not a CUDA kernel, but I stick it in here anyway. Only going to use this on my CUDA kernels, but the other kernels don't care. They're not going to use Z-CUDA stuff. They're not going to use any of this, but it doesn't hurt to be there. And the CUDA type is going to also work on int64 because I might use type punning. I might have there are cases where I can use the CUDA atomics on types that CUDA doesn't handle. but they're the right size. And if I pun it to say a 64-bit integer, maybe it's a 64-bit type, and all I need to do is do an atomic write to it, or whatever, it's something simple like that, or a swap or something. Well, then I can sometimes we'll just pun it to int64, and that's what the atomic type is. Here it's the same, but in some cases, if I need to, I'll pun the type, take a pointer, recast the pointer to a pointer to that type. This is all CUDA stuff. This stuff and OpenMP stuff, these macros did not appear here at all. In the MyCX, you didn't see them all. So what happens if I use them? Well, either they're not defined, or later on, or they'll be the empty string. If I don't define them here, what happens is I put in all these definitions for the monoid, or for the matrix, or for the operator, for the multiply operator, whatever definitions I need. Then at the very end, just before I go in and grab my actual templatized kernel code, I have this. All the monoids, all the reductions get that, monoid shared definitions. And this is a bunch of if and def. So like if something's not defined, define it as the default or the empty string or whatever. So this will do all the cleanups, the things I chose not to define up here, because this didn't have all this stuff about atomics. This will define Z as atomic as 0, probably. Like if I look for source include GB monoid shared definitions, like oh, if I haven't said that it has OMP atomic update, then it doesn't. It's false. So the MyCX Plus, even though it actually could be done with a floating point OpenMP atomic, because it's just a complex double, I think. Maybe it can't. Maybe complex. I don't think complex numbers can be. Oh no, I can. I can do it as two different. Yeah, a complex plus, if it's built in, I can do two complex pluses atomically for complex plus reductions. So this would be true, but if it's not, if I haven't defined it, it's false. So these cover any of the cases. This will handle all the special cases that I don't bother to define in the header file. If they're not defined there, I get these as the defaults. So that's what happens at the very bottom here. So this is the MyCX case. So now we're to creating all these macros. So now we're out of the binary operator. Let's go to the top level, GB macrofy reduce. What time is it? 2:30. Okay, 2:40. All right. So that was just that. All right. And then I need to produce the update method. Oh, no, I used the update. Now I need to produce this method. This method's only used in reduction to scalar. This is a macro that I want to do two things at the same time. I want to grab the value from the matrix and reduce it within the scalar. So this is just becoming like, this could be Z plus equals A times AXP. In fact, in the other method, let me just pull in both of these at the same time. I can switch between them. It's update, but this update is plus equals. So this turns into Z plus equals AX of P. So it's a single line of code, very compact. I'm hoping the compiler will be able to both load and accumulate at the same time or whatever. I mean, I'm giving the compiler as much help as I can, because sometimes the compiler will produce different code if it sees that plus equals than if it sees something like this. So I try to put in as tight as expressions as I can. And so if I don't have typecasting, I do this. If I have to typecast, I have to declare a temporary and get it. Declare a temporary, load it from the matrix, and then do the update. Because this get will do the typecast for me. Which get A was going to be defined down here. How do you get an entry from the matrix? That's how you get an entry from the matrix. It looks kind of obvious, but if it was ISO valued, I'd put a 0 right there instead of P. Okay, so what else is to do with so that's the monoid that produces to here, but now I have to macrofy the matrix, which is called by macrofy input. So this is, and I don't know, maybe I shouldn't go through all the details here, but this has to macrofy everything having to do with the specific matrix A. And if I have other matrices, I'll have a matrix C, a matrix B, whatever. No, A or B, not C. C is an output method, output matrix. Here, this, I put in a comment. So macrofy input is going to do all of this. And I don't know if I need to go through all the details. But this is everything having to do with the matrix data type in 64 and its data format, which in this case is bitmap. So A is bitmap is true. And then I have all these accessor macros, which I described way back, I don't know, session 1 even. What's a matrix? No, where is it?
Yeah, when we were talking about the formats.
Right, built in,
Yeah.
include GB matrix. Okay, all these little GBH, GBP, GBA, amphibics. Okay, well, every matrix here, the A matrix has its own P macro. It's bitmap. So how do you get where's the start of the column? Oh, it's just a multiply. So these are all data format, matrix format accessors. Do you have zombies? No, it's a compile time constant. Are you ISO valued? No, it's a compile time constant now. I have two types, the A and the A2 type. So this data type is going to be possibly have to be typecasted to match the input of the operator that's going to use it. In this case, it's just one operator, so I wouldn't have had to do this. And it's also the same type anyway. But the A matrix may have to be typecasted to either X, the X type, if it's not flipped, or to the Y type of the operator, if it's flipped. If it's being passed to an operator that's been reversed and it's not commutative. So when I load in A, I'm going to cast it to something. What do I cast it to? X or Y or Z or blah, blah, blah. It's the A2 type. What does it go to once I load it in? And so when I load it, when I actually declare it, this will actually be, when I load it, I'll cast it at the same time. So that'll actually be the after typecasting type of A once I load in that scalar. So these two types are going to match. So yeah, everything having to do with accessing that matrix will be right there. And I have one last little thing for the macrofy reduce is the panel size. So this is now controlling, it's one number. Okay. So this is a definition that is going to depend on the monoid. I probably should have put it up at the top under the monoid. I didn't because it's not really part of the monoid. It's only needed for reduce because the matrix multiply is not going to use this. What's this panel? Well, my reduction methods, some of them are panel based. Even a single thread will not just do Z plus equals blah, blah, blah over and over again, looping across its part of the matrix. That's slow. It's faster to load in a bunch of entries and reduce all of them to a temporary array of 32 words, 32 data types. Right? In this case, it's in 64s. Okay, and then iterate in chunks of 32. And at the end, do a reduction across those 32 with plus equals scalar. So it's a vector reduction. The reason that's better is just the compiler, the hardware likes that better. There's no dependency between operations. They're all independent. So the pipeline works better and it's way faster. However, the panel size depends upon the data type and the operator. So this is what this logic, the best one. And I've kind of played with it. It's like, how big should the panel be? Well, if you're Boolean, it turns out that it's 8 bools. I don't know. I've just tried different cases. If you're min and max, I've tried 16. If you're these monoids, well, it depends on the data type. These are really wonky numbers. But that's what I found, is that the floating point, when viewing these with floating point, like plus times, the panel sizes are different. And then, I mean, this is probably specific to an Intel processor because that's where I've optimized it for.
Yeah, for sure. That seems to be, any kind of voodoo number is some
It's a
platform
voodoo, yeah.
dependency.
It's
Yeah.
probably a platform dependent voodoo number. And okay, if I was clever enough, if I benchmark across a bunch of processors, I could determine, oh, for an Intel processor, I could have an if-def here. I do have a detection of the hardware you're compiling for. I could have an if-def to say, oh, if you're AMD, this is 64. If you're Intel, it's 32 or something.
Or have
Or
some
if
sort
you're an
of auto,
ARM.
yeah, have some kind of
Yeah,
auto tuning function.
yeah, exactly. I want to have a compile time number though,
Yeah.
but I got to have a compile time determination that's dependent on the architecture here. I don't. I just have a number. I figure, 32 for plus double. I mean, if it's not, these numbers are not so sensitive. I figured if it's an ARM, it's not going to be so different. But I've not tuned it for an ARM. I just, run out of steam, and so that's what I've tuned it for these cases. So that's the panel. If the panel size is 1, so if you look at this method, this is the actual the method. Okay. Now, once I've macrofied it, I'm going to compile it. That's the whole macrofication. Now I've got to compile it. Well, I've only done the macrofication down to here, but let me look at the template really quick. Let's see, reduce template GB JIT. No, it's not reduce template. Where is it? Oh, no, it's a JIT kernel. GB JIT kernel. JIT kernel's template. Oh, CD. I'm not doing a VI. There we go. That's why it's not finding it. Reduce. Here we go. Okay. These are all comments. If-def comments only. I'm basically replicating this file and explaining how this all works. This is not necessary. I'm just kind of giving you an example. In fact, it looks like almost this very example. Different hash code is different. Okay. This is the actual kernel code. The prototype, grab the scalar, grab the workspace. If you have any zombies, don't use the panel because I have to do a test anyway. It turns out to be faster because that's, or if you're bitmap, it turns out I have to do a test, so it doesn't help with the panel. Or if the panel size is 1, then I use a panel-free work method. Otherwise, I have a panel type reduction, and it's different algorithms. But it's not a compile time. It's 32, so it's going to come down here. Well, unless I have zombies. Do I have zombies? Oh, no, I don't have zombies. Good. It'll come down here. So this algorithm here is zombie free. It knows there's no zombies. And it doesn't also does not have to handle the bitmap case. But this one has to handle the bitmap case. So 2 reduction algorithms just stuck in the kernel. I could have called it, you know, a different kernel, I suppose. I could JIT it 2 different kernels, but I have the kernels, the 2 algorithms inside the kernel, just chosen with at compile time. So that's the template right there. So I left off here. I jumped ahead a little bit. So let me go back to, and it's almost 3 o'clock. We're getting to a stopping point pretty quick. Jitifier. We looked at the macrofy reduce. Okay. So we got to here and then we're done. Okay, done. That's the end of the macrofy for reduce. Now we're back to macrofying everybody because everybody's going to have the next stuff. Let's go to GB, back to, I think, is it here? Oh yeah, here. I did the family. I took us all the way to this line of code that all this that's highlighted I've produced with this line of code. This is just a switch across a bunch of macrofy per family. Macrofy reduce is one family. Macrofy MXM is a family of all MXX kernels. There's about 8 of them. Now I have the rest. That's going to produce these 2 pieces. This piece right here. Okay. This is, and I'm sorry, let me make this a little bit bigger. This piece of ifdefs, what is this doing? This is defining the difference between a JIT and a pre-JIT kernel. The JIT kernel is, when I compile a JIT kernel, I set GBJIT runtime because I'm compiling it at runtime. It's truly a JIT kernel. In that case, the name of the kernel, like if I looked at the, what is it? JIT kernels template GBJIT kernel reduce. The name of this kernel is by default just GBJIT kernel. That's the name of the kernel. Every JIT kernel, if I look at the library.so file, if you ask what functions are in there, there's 2. Always called GBJIT kernel and always called GBJIT query. That's all that's there. Now, but if you copy this file, the source code, into the pre-JIT folder in GraphBLAS and build GraphBLAS, then each of these functions needs its own name. And there's the name. So when I'm compiling at CMake time and GraphBLAS build time, not JIT runtime, but GraphBLAS build time for the GraphBLAS library itself, this is not defined. And so I'm going to rename this kernel with its name, which is GBJIT reduce ACF1F882. This one, there's its name. Its name will match its file name, which makes sense. Unless you're the query method, then I tack on the word query. So that's this method. The GBJIT query is just slapped right here. There's the source code for that entire function. I don't have a template for that. I just slap in all the definitions there. I have to build now the query function, which I haven't shown you yet. So this code here that's producing this, where was it? Here, no. I'll just pull this in again. I must have left there. Here we go. This code. I have to stick in the JIT pre-JIT selection for the name. And now I have to put in the query function. So I have a function called macrofy query. The goal of this function is to produce this. Oh, I've already produced this. Okay, where did I produce that? Let me do that first. That is right here for everybody. For CUDA, for MXM, for reduce, everybody gets that same definition right there. I include the template source. My codes are very carefully named such that this just works. %.%. What is this? This is the K name, which for reduce, it's quote reduce. That's the name of the kernel. If it was CUDA reduce, this would be called CUDA underscore reduce. And it'd be, instead of .c, it'd be .cu. And that's it. So that I just have a consistent naming scheme of all my templates such that this can then produce it. Okay, now I produce the query.
Yeah,
And
just
the
to let you know,
query,
I got a hard stop at the top of the hour.
okay. Well, short, yeah, we're at a really good stopping point. Basically, I have to produce the query function, which is going to produce, say, this. It's going to say, okay, I want to ask the kernel, if I've already compiled it, what's your hash code, just as a sanity check? What version of GraphBLAS are you? 9.3.0. Well, give me your strings, 5 of them, 2 operators, no, possibly 2 operators, possibly, or 3 operators? No, possibly 2 different operators and possibly 3 different types, I think. And then give me your, check the identity value in the of the monoid and check the terminal value of the monoid. And if any of those are different, I'll detect it. I'll either pass the strings and do the string compare in the caller, or I'll check the value right here and pass it in and have this current function check it for me. So
And we
that's what the
covered
query
this
function.
in the last session too, the query
I
function.
think, yeah, but this is
Yeah.
where I'm generating it basically.
I get you.
And it's pretty straightforward. It's pretty straightforward. So
Cool.
yeah.
Well, so let
I
me stop the
produced the
recording.
file. Yeah,
Oh,
we'll
no, you're
stop
good.
here. Well, what I need to do next is, now we've written the file, we got to go compile it and load it in.
Okay.
I haven't done that yet.
So that'll be the next session, session 7.
Next session, how do I compile a kernel and
Session
hash
6.
it?
Yeah.
Yeah, compiling a kernel and hashing it.
Well, that'll be our halfway